What's up, pre-calculus students? Here's your Unit 9 review video. This entire unit's to be done without a calculator, or else it'd be easy. So let's get to it. We had 3 lessons. First lesson talked about behavior of a polynomial, bounces through zeros, passing through zeros, bends through zeros, also end behavior. Second lesson, we had inequalities, which used our knowledge about the behavior of a polynomial to help you solve the inequality. And then the third lesson, we switched into rational functions and rational inequalities. That's when we need to find both zeros and undefined points, look at multiplicities, look at a sign analysis to be able to answer the inequality correctly. We started with polynomials and what the behavior or what the shape of polynomials were. End behavior is like what's going on at the ends. Like as x goes to negative infinity or as x goes to infinity, what are your y's doing? Are your y's going up? Are your y's going down? Are your y's going to a number, which could be seen in the future? But for right now, we typically have answers for your y's as a positive or negative infinity. So here I'll start as x approaches negative infinity. My y's equaling to f of x's. So as I go to the left, my y's are going down to negative infinity. So this would be the correct notation for the end behavior on the left. If we go to the right, as I go to the right on my x-axis, my y's are also going down towards negative infinity. What does the end behavior tell you about the leading term of f of x when written in standard form? 2 things. We know about odd functions, which have this type of end behavior. It's the John Travolta positive or John Travolta negative. I'm not sure how it looks like for your camera. I think this is John Travolta positive. This is John Travolta negative. And that's for odd. So y equals x, x cubes, x to the fifths. And then you got even. Y equals x squared. We know is going up, or y equals negative x squared going down. So either our touchdowns or our angry gorillas. So since our end behavior is down and down, we got an angry gorilla. We're going to have some sort of even degree. I know it's going to be more than 2 because of all of these turning points and all of these different zeros. So I know it's going to be x to some even. I can do the analysis for what it is, and probably a little bit later. And I know that the leading coefficient is some sort of negative number. So this would be like the leading term of my function, some negative number x to the even power. That's all we can work with right now. We'll go back to filling out what we think the even power could be at least, based on looking at the multiplicities of our zeros, also the amount of like turning points that we have. What are all the roots? So the roots are zeros, x-intercepts, all the same. Intercepts. Same as a root. So it's when our graph crosses the x-axis. So I got x equals negative 3. Now I know the multiplicity of this has got to be an odd number, and it's got to be at least 3. That's because I'm bending on the way through. If you think about y equals x cubed passes through the x-axis, but on a bend. It just like has the same behavior as y equals x. It just goes quicker towards 0, slows down, and then quicker away from 0. It could be 5, it could be 7. We don't know. Let's just assume it's like 3. We got x equals 0. This has a multiplicity of 1 because we're passing through. Y equals x, y equals negative x, passes through the x-axis. No bends. And we got x equals 2. The multiplicity has to be even because it bounces. If you think about y equals x squared, that graph bounces off of x equals 0, does not go into the negative land. So I'm going to say it's even. I'm going to assume it's going to be 2, but it could be 4, it could be 6, 4, 6, 8. They're all bounces. Now, we are told this is a 6-degree polynomial. So actually, hey, this has definitely got to be 6. What is the equation for f? Well, we could start out understanding that our roots mean our zeros of our function. If x equals -3 makes our function 0, that means a factored form, one of the pieces of our form, has to be x plus 3. That's because if I plug in -3, I'm going to get a 0 for my y passing through. Multiplicity, I'm assuming, is 3. If I do a 3 plus a 1 plus a 2, that gets me to a degree of 6. That works out well. So my assumptions of 3, 1, and 2 are correct. X has a multiplicity of 1. So x equals 0 has a multiplicity of 1. So if I have x as a factor here, when I plug in 0, this entire product is going to be 0. So this would be a piece of my form. This is in factored form. Then my other 0 is at x equals 2. Its multiplicity is 2. So that means I'd have to have a factored piece of x minus 2, so that if I plugged in 2, I would get a 0 for my y. The multiplicity is 2, so I'm plopping a 2 right there. This works out, 6-degree polynomial. If I distributed everything, I'm not going to do that because it'd take me too long. But if I did, I would have some x to the 6, and I have an x times an x cubed times an x squared. So x cubed, x squared, 1, 2, 3, 4, 5, 6, x to the 6. Okay, and I think that this is correct. However, we got to remember our end behavior is down and down. We are angry gorillaing. So that means my leading coefficient has to be some negative number. Now, how we figure out this negative number are two different ways. If we are given some point, some sort of xy point, we could plug in that x, plug in the y, and solve for this a. We'd find that it's negative. I'm not given enough information here to be able to distinguish what a is because I'm not given any y values here. I just know I'm going to have a 0 here, a 0 here, a 0 here. So I am not 1000% sure what it's going to be. I don't know for a fact that it's going to be -1. So we can just leave this as like some negative number. If this is a multiple choice question, you'd pick the negative number times x plus 3 cubed times x minus 2 squared. Okay. Question number 2, we have the polynomial. We're asked to graph it, at least understand the shape. We don't have to be perfect in terms of locations of things, just the shape and the zeros. We see that it's an x cubed. This is going to dominate in terms of what the function is doing towards the ends when we plug in infinities and negative infinities. X cubed, odd power. We have our John Travolta's, positive leading coefficient. We're going to end up just like y equals x cubed, up and to the right and down and to the left. So as our x's go to negative infinity, as our x's go to negative infinity, my y's are going to be going down to negative infinity. As x's go to positive infinity, my y's are going to go to positive infinity. Right there. Write the function in factored form. Okay, lots of factoring in this unit. No calculators. Always good to try to find a greatest common factor. To pull that out first, I can pull out a 3x from all three of these terms. So that's dividing. It's the opposite of distribution, which is multiplying. So if I divide 3x by this, I'm left with x squared. If I divide 3x out of that, I'm left with 4x. If I divide 3x out of that, I'm left with a 1. I feel like we should have something else actually for this function. The reason why I think that is because I can't factor this, which is not nice. If you have a quadratic that can't be factored, you should be thinking about using the quadratic formula to find the zeros. Opposite of b plus or minus the square root of b squared minus 4 times a times c. All over 2a, which gives me 4 plus or minus root 12 over 2. You're not going to be using the quadratic formula, in my opinion. I know from AB calculus that you don't use the quadratic formula hardly ever. So I'm actually going to change up this function so that we can factor it, just so it's easier to look at. And the ones that you're going to be given on your test, I have to double check, but I don't think you're going to be using the quadratic formula for your test. Everything's going to be factorable. So let's see. Let's go -3, -1. So that'll be a +3. So this should be like a 9x. So change that for me, just for fun. If I pulled 3x out of 9x, I'd have a 3. I can factor this 3x, x minus 3, x minus 1. That's the two numbers that add to get -4 and multiply to get 3. And that's like a fully factored form where I don't have to use the quadratic formula. Again, don't stress about the quadratic formula. I'll put it up on the board for your test, but I'm 95% sure on your test everything will be factorable. So you get nice whole number roots. So the nice whole number roots here are 0. Plugging in 0 makes this 0. Plugging in 3 and plugging in 1. And the multiplicities of all of these are 1. You can see like the powers are all 1. The y-intercept occurs when x is 0. It's like that one extra point that is easy to find that we want to find. So when x is 0, whenever my cursor comes back, when x is 0, my y is going to be 0. Not always the case. If there was plus a number, it would be different. But from there, we could sketch. We have the point 0, 0, 1, 0, 3, 0. We know the multiplicities are all 1, which means we have passing through situations for this positive leading coefficient x cubed. We don't know how far we go up and down in between these zeros. I don't know where this is going to be. I don't know where this is going to be. You will know where those are when you get to calculus, how to find the locations of these maxes and these mins. But for right now, just general shape is all that's needed. And this would be your sketch of the graph of 3x cubed minus 12x squared plus 9x. We're doing the same thing here. It's nice that it's already in factored form, so we can easily identify the zeros, the roots. X equals 0, multiplicity of 1. X equals -2, multiplicity of 2. X equals +2, multiplicity of 2. Passing through, bouncing. Now, if I were to distribute everything, I'd have an x squared, and an x, which would give me some x to the 5th. This negative leading coefficient would stay. So I know that the first term of this polynomial, after distributing everything, would be -x to the 5th. This helps me with my end behavior. I know we have a negative odd power with the negative John Travolta end behavior, negative x cubed end behavior. We'll plot our zeros. We have a y-intercept at 0 as well. So I know I have this point. I got -2 with a multiplicity of 2. I got +2 with a multiplicity of 2. So what we do is we are going to bounce off of -2. We'll pass through 0. We'll bounce off of 2. And this is what my function will look like. Now, for the review, you won't be able to do this on the test unless you cheat. You can graph to check this. For the actual test, you just have to have confidence in your analysis of your function. So let's see, is my shape going to be exactly what I expect it to be? Bounce, pass through, bounce, boom. Okay, perfect. This guy, my leading coefficient, if I distributed everything, would be 3 times x times x times x squared. So 1, 2, 3, 4 x's, 3x to the fourth, plus a bunch of other stuff that we don't care about. Helps me with my end behavior. We have a positive even degree. We are talking about touchdowns. Easy to find the zeros. The zeros are going to be at x equals -3, x equals 2, and x equals 5. Multiplicities of these are 1, 1, and 2, which are telling me pass through, bounce. Y-intercept, when x is 0, is not going to be 0 anymore. It would be whatever h of 0 is, plugging 0 in for x, I get 3 times -2 times -5 squared. That is not a nice number. It is 18 times 25, which is a large number. That's negative. -450. Great. So I do have a point 0, -450. Great. All we expect you to do is find that y-intercept as that one extra point. Plot the zeros with their multiplicities. I got 1 at -3, 1 at 2, 1 at 5. We are going to pass through -3. Go all the way down to -450. Pass through -2, or pass through +2, bounce off of 5. All right. It's probably going to be a little bit more extreme than that if I graphed. You'll see like sharply going through things. Yep, later, you're gone, you're back, you bounce. If I plugged in 0, I got that y coordinate of -450. Passing through, going through -450, passing through, bouncing off of. All right. All right, here is a situation where I'm going to be able to find the specific function that gives us j. We are going to assume that all of these zeros, x equals -4, x equals -1, and x equals 3, have a multiplicity of 1. Okay? We also have an extra point. Our y-intercept is at 0, -3. That will be used. My j of x function is going to be some sort of a value, some leading coefficient, times all of these factored roots, x plus 4, x plus 1, and x minus 3. Now, it's going to be easy for me to find a right now. I could find it later. It doesn't really matter. Plugging in 0, -3, I'll find a. 4, 1, this is plugging in 0 for x, y being -3, 4, 1, -3. I get -3 equals a times -12, so I get a is positive 1/4. I didn't like assume a was positive or negative based on the end behavior. It's just like you will find a, and it will be the correct positive or negative value. Now, we don't want factored form. We want standard form, which means like fully distributed. So let's get out our distribution tools. I don't like to use the box. I like to just do these two at a time. I'll start by multiplying the x plus 1 and x plus 4. I'm doing this down here, and then I'll be able to do the end behavior. I mean, we can see what the end behavior is, so we don't have to really worry about b. I'll get that later. Leave the 1/4. This becomes x squared plus 5x plus 4. How did I do that so quickly? Well, it's like we know that when we factor something, x squared plus 5x plus 4, we're looking for two numbers that add to get 5 and multiply to get 4. If you want to distribute two binomials quickly, just add these two numbers. That's going to be your middle term times x. And then 4 times 1 gives you your end term. If you're not comfortable with that, go one step at a time. X times x is x squared. X times 1 is 1x. 4 times x is 4x. 4 times 1 is 4. 1x, 4x, 5x. But now I need to multiply the x squared plus 5x plus 4 times the x minus 3. And then I'm going to finish off by distributing the 1/4. So let's work here. You could box this. Some people like the box. I just like to distribute. X squared times x, x cubed. X squared times -3, -3x squared. 5x times x, 5x squared. 5x times -3, -15x. 4 times x, 4x. 4 times -3, -12. Giving me 1/4. I got 1x cubed. I have a total of 2x squareds. I have a total of -11x's. And then minus 12. If we want to, we can then distribute the 1/4. I'm not sure if it's going to be required or not, but let's just be ready for both. 1/4 x cubed plus 1/2 x squared minus 11/4 x minus 3. If I graphed that, I'm going to see exactly what I see in the picture. You won't be able to do this on the test because you can't use a calculator on the test. Beautiful. We got our zeros. We got our y-intercept. Looks good. End behavior, might as well do that. As x goes to negative infinities, our y's are going to negative infinity. I guess this is j of x, not f of x. As x goes to positive infinity, j of x is going to positive infinity. As x goes to the right, the y's are going up. All right, great. We're going to leave this in factored form. Hooray. We got a y-intercept. We got some zeros at -6, at -2, at 1, and at 5. You can just use y here. It doesn't say to pick something. So some a value. X plus 6 must be a factor because -6 plugged in will give me a 0. Multiplicity is 1. X plus 2 must be a factor because -2 is a 0. X minus 1 is probably going to be squared because we're bouncing off of 1. and then x minus 5 to the first power. We have a 0.05. This is how we're going to find our leading coefficient. It's going to be a negative number, I know that, because of the end behavior. It's like that negative x cubed. So if I plugged in 5 for y and 0 for x everywhere, I will solve for a. I will get a negative number, which will confirm kind of my suspicions. A times 6 times 2 times -1 times -5 is not a nice number. I'll divide both sides by 5, and I get a 1. The -1 and the -1 will go away to be a +1, so that's not that bad. I get a times 12 equals 1, a equals 1/12. So I believe my equation is 1/12. I'm not even going to rewrite it. I'll just say a is 1/12, and I'll say 1/12 goes over there. I'm going to double check because I can. X plus 6, x plus 2, x minus 1 squared, x minus 5. I'll adjust my window so it's just like this, where we go from -10 to 10 on the x and -100 to 100 on the y's, and we should see the exact same graph. Uh-oh. What happened? Did I not put -1/12? Nope. Why didn't I get -1/12? Hold the phone. It's -1 squared, team. Oh, we got to pay attention to our multiplicity. Man, good thing I was able to check. I should have known that. Because I knew, like, I was going, I even just said in the video, I'm going to get a negative number. And then I didn't, and I wasn't even paying attention. So pay attention. The 5 goes away, but it does leave a negative number. Switching this to -1/12. You guys know about insert? Y'all don't know about insert. Insert a negative. Now we're good. Looks just like this guy. All right, now we are going to use our knowledge about multiplicities or about the shapes of polynomials to answer the following questions about inequalities. When is x squared minus x minus 6 less than 0? That is when we have negative values, when we are below the x-axis. When do we have negative values is like between 0 locations. So zeros that we've been finding, these factored forms, these x-intercepts, are very important when it comes to inequalities because they'll tell us like when we could possibly change signs. So just like when solving equations, we're looking for like zeros of polynomials for inequalities as well. So we look to factor to find our zeros, and we'll put those zeros on a number line. You could either sketch the entire function. I like to use a number line because once we get to like rational functions, you don't really know the shape of the rational function yet. In calculus, we'll be dealing with lots of different types of functions that students don't really necessarily know the shapes of them. So it's best to just maybe use a number line and use our knowledge of multiplicities, or use our knowledge that if you found all your zeros, your signs are going to be consistent on all of these intervals. They're either all positive or all negative. All positive or all negative, all positive or negative. They're not going to change signs because if they were to, you would have another zero. What I like to do is use a test point, and I like to start all the way on the right. It's because usually it's like easiest to find the sign. I don't care what the value is. I just care about the sign. If I plugged in 4, 4 minus 3 is a positive. 4 plus 2 is a positive. A positive times a positive, I know, is a positive. I know for a fact that all the values are going to be positive. Now, instead of sketching this polynomial, I'm just going to use the fact that I know the multiplicities. And multiplicities talk about if I change sign or not, if I bounce or pass through or even bend through, but you're still changing sign. So since these zeros have multiplicities of 1, I know I'm going to change sign. I use this with rationals as well, the idea of the multiplicity. When are we less than 0? When we are negative. Here are our negatives. We are not going to include our zeros at -2 and 3. You need to be prepared for both interval notation and inequality notation. X is between, X is belonging to -2 to 3, this interval, or X is between -2 and 3, like that. Okay? And all the others fall along with that idea. Find the zeros. Here we're looking for greater than 0. Positive values are greater than 0. Oh, I'm going to attempt to factor out a greatest common factor. I can't. So what I'm going to do is hope that this factors by grouping well. Remember, split this into 2 groups of 2. Factor out the greatest common factor of each individual piece. Your attempt is to have the factored out binomial to be the same. So I can factor out a 8 from this. I can do a 16 out of this. That's what I'm looking for. And I'm going to factor out a -16 so that I have a positive 2x minus a 3. If I did 8, I would find that I could factor out also a 2. So 8 would give me -4x plus 6. And then the 4x and the 6, I could pull another 2 out. So the 8 and the 2 would combine to be 16. Best to find the greatest common factor from the beginning. Now from here, from this factored form, since these are the same, I could factor out the 2x minus 3 from both of these terms separated by this addition. I like to keep the addition and change it to add an opposite. That way I know that it's going to be x squared minus 16. Now we find out that x squared minus 16 can be factored. It's a difference of perfect squares. Or you could think about it as x squared plus 0x minus 16. There are 2 numbers that add to get 0 and multiply to get -16. It's 4 and -4. So I can rewrite this as 2x minus 3 times x plus 4 times x minus 4. Giving me my zeros, my possible sign change locations, -4, 4, and then 3/2, setting this equal to 0, which is 1 1/2. All of these multiplicities are 1, maybe listed off here. That way you know your signs are going to change. Don't worry about sketching. If you just test one point and then use your multiplicities, you can then fill out the rest of your signs. I'm going to test 5. That says test 5. 5 times 2 is 10 minus 3, positive. 5 plus 4 is a positive. 5 minus 4 is a positive. All positives. This is going to be positives, and all of my values are going to be positives. That's what my graph will look like. It'll pass through 4 and go up towards positive infinity. I will change signs everywhere else because of the multiplicities of my zeros. I'm looking for positive values that are also equal to 0. So I will include -4. I will include 3/2, and I will include 4. Writing this out in interval notation, I'd say x belongs to including -4 and 3/2, close brackets to include, or include 4, go to infinity. We don't like to say you can ever equal infinity. It's more a concept, so we have an open bracket around infinity. Inequality notation, we are between and equal to -4 and 3/2. We are bigger than or equal to 4. Okay. Same deal. This is a little bit easier. No, it's not. Maybe we do need to prepare for the quadratic formula. Two numbers that add to get positive 3 and multiply to get 8. Doesn't exist. If it was other numbers, it would work. So, Mr. Quadratic Formula, or completing a square. Completing the square would not be nice. Negative 3 plus or minus the square root of b squared minus 4 times a times c all over 2a. Oh, this is a good one. And it's not because it can't factor, it's because I'm using the quadratic formula to realize something. This, inside of this quadratic, I realize that it's going to be a negative. It's 9 minus 32, which is negative 23. I think that's right. Can't think right now. Okay, so that's a negative value inside a square root, which means my solutions are going to be imaginary, which means this guy, and now that you think about it, it makes sense, will always be positive. The graph of x squared plus 3x plus 8 will always be above the x-axis. This shows you that you will not have any real zeros. So this is always all positive or all negative, depending on your leading coefficient. Pay attention to that. Since this is a quadratic opening upward, all of our values are positive. X can be any number. Plug in any number, and I guarantee you that this is positive. I'll leave it at that. This is nice because it's already factored, so I can just visualize and see my zeros are at negative 2, but its multiplicity is 3. Pay attention to that. 1, its multiplicity is 2. Pay attention to that. That means we are not going to change signs at 1. We're going to bounce off. Now, you could sketch the graph to get that shape and just see the bounce. Or what I like to do, what you'll do in calculus, is use a test point, like 2. If you plugged in 2, you get all positives. Positive times a positive, so that's positive. You will bounce off 1. You will not change signs. You will bend through, but you will pass through negative 2. You will change signs. You are looking for greater than or equal to zeros. That's positives. So that's including 1. That's including negative 2. Really, it's all of our values that are bigger than negative 2. So from negative 2 to infinity. Or x is bigger than or equal to negative 2. Interval notation. No, this is good for inequality notation. Interval notation, you could say negative infinity to infinity. All right, now we switched into rational functions. And the key with rational functions is the idea that we don't necessarily have to have a 0 to change signs. Rational functions have these things called asymptotes. For example, y equals 1 over x. Now, when x is 0, we have 1 over 0. 1 over 0 is undefined. It's not a 0. It is actually the indication that we have a vertical asymptote. Whenever you have a number divided by 0, this is an indication that you have a vertical asymptote. We can talk about why more. It's like numbers divided by things that are very small or very big. So we'll be going towards negative infinity or positive infinity close to this value. So look at y equals 1 over x. It goes from negative values, but then it switches signs to positive values at this vertical asymptote. So when dealing with rational functions and inequalities, we still want, our number line. We still want our possible sign change locations. But our sign change locations could be at undefines or at zeros. Undefines, again, are when your denominator equals 0. and you have just a number in the numerator. Zeros, when your fraction equals 0, is when you have a 0 in a numerator and a number in the bottom. One thing we have to worry about, though, are situations when we have zeros in both the top and the bottom. Now, we will talk about this more in the next unit, why this is a whole. Now, what will show up in the way I teach my students is that you'll see the multiplicity of the root will be even, which means you will not change signs at a whole because the multiplicity will be even. Yeah. So be wary about that. I'll show you how I do it. We will find when our denominator equals 0. All right, that's at 0. So at x equals 0, my denominator is 0, so my fraction is undefined. It's an asymptote. I'll set the numerator equal to 0. Now you can add 1 square root and you get plus or minus 1, or you could factor this, x plus 1, x minus 1. Negative 1 and 1. Multiplicities of these are all 1. Like this occurs once, this occurs once, this occurs once. Keep track of that. It's nice to have the entire fraction in factored form to maybe find things. Like you could have just factored at the beginning and then just found all of the top and bottom zeros. It's fine. I like to do it kind of separately just so I keep track of like, okay, undefined versus zeros. But we actually can use this guy when we use our test points. Like I'm going to test 2. It's not about the number, it's about positive or negative. Positive times a positive divided by a positive is a positive. Since the multiplicities of all these are 1, we will change signs. We'll pass through 0. We'll get to an asymptote. We'll trend towards like negative infinity to the right of things. We'll change signs. We'll pass through a 0. We'll change signs. When are we greater than 0? That's in Mr. Positive land. Mr. Positives are here and here. We're not including any zeros, so x's belong to negative 1 to 0 and 1 to infinity, or 1 to infinity. Inequality notation, negative 1 to 0, x is bigger than 1. Okay? Cool. I don't think we're going to have any holes the rest of the way, which is nice, but we do have tougher ones. Just like with polynomials, zeros, undefineds, having everything on one side equal to 0, crucial. So even though it looks like I want to multiply both sides by x minus 5 and put everything up, it actually like eliminates one of my solutions, which is like 5 as a possible sign change location. So since it's an inequality, get everything onto one side. I know a lot of us like instincts are to multiply by x minus 5. Don't do it. It will remove 5 as a solution if you do that. So instead, we subtract the 3 from both sides. Now, to be able to get some fraction less than or equal to 0, we need to give this a common denominator. Now, let's recall common denominators. If I have like 3/4 minus 3, what do I have to do to subtract 3 from 3/4? Well, I have to turn this 3 into a fraction, multiply the top and bottom by 4 so that I don't change it, but I make it look different. And then something that a lot of us forget is that when you're subtracting fractions, it's almost like subtracting like terms, like 3x's minus 12x's. 3x minus 12x is negative 9x. 3/4 minus 12/4 is negative 9/4. The 4 doesn't change. So, especially with adding, some people like to add like the 4 and the 4 and make it eighths. Don't do that. So that's what we're doing here. We're turning this into a fraction, and then we need to give it the denominator of the other guy. Now, to do that, though, I need x minus 5 to be given to 3. Multiply the top and bottom. so that you don't change it. You just make it look different. Now, this is where like a lot of algebra comes into play. Showing work helps. Making sure we don't mess up when distributing negatives helps. This is very much like stuff we do a lot in calculus, a lot of algebra. I keep the negative. I have 3x minus 5. Now, maybe a good idea would be distribute this negative. That way, you would distribute the negative so that it's negative 3x plus 15. It's up to you. Regardless of what you do, you need to make sure that when you combine your two fractions, again, the denominator does not change. It's like terms. But you have 2x's minus 3x's, which is negative 1x. You have negative 7 plus 15, which is positive 8. This is less than or equal to 0. We are now set up where we could see 5, definitely important because it's when the denominator equals 0. It's a possible sign change location at an asymptote. And then 8, actually, I got to put 8 over here. 8 is a 0. It's when the top is 0. 5 is an asymptote. It's an undefined. It's a sign change location. It's when the bottom's equal to 0. It's a good time to use a test point. Let's watch what happens when I plug in 9. Negative 9 plus 8, that's a negative. 9 minus 5, that's a positive. A negative divided by a positive is a negative. Now, these roots occur just once. I know for a fact, because of the multiplicities, that we will be changing signs. You could test 6. If I test 6, positive, positive, positive. Test 1, positive, negative, negative. You could test all your intervals if you want to. I like to use multiplicities. We're looking for less than or equal to 0, less than or equal to 0, here and here. We're not including 5. We would include 8. All important stuff. So x belongs to negative infinity to 5. Do not include 5 or include 8 to infinity. Inequality notation, x is less than 5 or x is bigger than or equal to 8. Last one, 3 things going on. Move it all on the one side and then take your time. We need a common denominator, but the common denominator has got to be a combination of the x minus 1 and the x plus 4. This is a problem my students need to try to do on their own. Okay, this is a problem you're going to see on the test. You have to be prepared to do all of the steps to get this right. First thing I'm going to do, because I like to, is distribute the negatives. So it's negative x. You don't distribute it everywhere. Maybe that's not a good idea because some people like to distribute it to all things. It just gets distributed in the numerator. So maybe if you don't understand that, don't like to do that, don't. Maybe leave the negative and worry about it later. Now, a common denominator to be able to combine all of these terms would be x minus 1 times x plus 4. If they all had x minus 1 times x plus 4, we could combine all of them. Which means I need to give this guy the other's denominator. I need to give this guy's denominator. I need to give this guy both. Okay? Let's see what I get. I'm going to distribute when I can, just so I can skip a step. 3x times x is 3x squared. 3x times 4, 12x. Minus x times x is x squared. X minus 1 is minus x. Pay attention to details. Minus. Okay, let's do this on the side. 3 times x plus 4 times x minus 1 is x squared minus plus 3x minus 4. The 4 and the negative 1 will combine to be positive 3x. The 4 and the negative 1 will also combine to be negative 4. Multiplying everything by the 3, I get 3x squared plus 9x minus 12. This is over x plus 4x minus 1. This is x plus 4x minus 1. I'm not going to distribute this. Why? Because I need to have it factored to set the denominator equal to 0. Okay, now I'm going to combine. Distribute the negative to all of your terms plus a negative, a positive, plus a negative, a positive. Let's see what I get. How many x squareds do we have? 3x squareds, negative 3x squareds, and a negative x squared. I'm left with just negative x squared. Okay, those are gone. 12 x's, 9 x's, x. 12 minus 9 is 3, plus 1 is 4. 4 x's, the 12x, the x, the negative 9x gone. Notice I'm taking my time. I'm being careful. Plus 12. Okay. To factor the negative x squared plus 4x minus 12, I'm going to factor out a negative 1, but it's not going to disappear on me. So let's move this up here. Factor out a negative 1, and I have x squared minus 4x minus 12. Two numbers that add to get negative 4 and multiply to get 12. Negative 6 and positive 2. If I'm doing this correct, I kind of can see like this problem is set up in a way so that you're going to have to simplify stuff and you will be able to factor in the end. X minus 6, x plus 2, x plus 4, x minus 1. When is this less than or equal to 0? Okay. We now have all of my zeros and all my undefines, all my possible sign change locations. I got positive 6, got positive 1. I got negative 2, I got negative 4. Positive 6, negative 2 are zeros. It's when the numerator equals 0. Negative 4, positive 1 are my undefines. It's my asymptotes. It's when the denominator equals 0. Let's use one test point and understand all the multiplicities are 1. We don't have wholes here, so we don't have to worry about multiplicities of 2. We'll talk about wholes more in the next unit. Let's test 7. This negative 1 is important. 7 times 7 minus 6 is positive. 7 plus 2 is positive. So I have a negative in the numerator, and then I have positives in the denominator. You'd have a negative divided by positive. That's a negative. We will change signs everywhere. You could use test points to do this, but multiplicities work because the multiplicities are all 1. I'm gonna double check this at the end. I'm gonna show you another way to. I'm not gonna show you another way to do this, so that you don't think about cheating. When are we less than or equal to 0? When we're in negative land. Here including there, here including there. So if you want to write that out, x's belong to negative infinity and negative 4, or negative 2 to 1, don't include 1, include negative 2, 6 to infinity, or 6 to infinity, include 6, don't include infinity. Inequality notation, x is less than negative 4, or x is bigger than or equal to negative 2, but less than 1, or x is bigger than or equal to 6. Ooh. Good stuff. We used to put 3 extra lessons on top of this one to be one big Unit 9. I'm glad we split this up. This is a good place to stop. Make sure we practice all of our algebra that we got from 7 and from our 3rd lesson. Very important, moving into the next unit. The next unit is all rational functions. We are going to be sketching rational functions. This is a good start, understanding sign analysis of rational functions. So don't think that you can just care about the first two lessons and just blow off the third, or just do the easy ones of the third, because the next unit is all lesson 3 uh, rational functions and analysis of them. Peace.